Welcome back to ECE 501B. We're starting I guess it's a good thing that we're finishing up the semester because we're starting a procedure, or maybe, hopefully we aren't, but we're missing this Wednesday also as far as in class, but I will provide you with the material, notes, and lecture material that you can watch at your leisure or when you want to make that day happen. But tonight is homework number 7. That one's due. Homework number 8 is due on the 7th, which I believe is a Monday. The deliverables for your project, which the main deliverable is deliverable number 2, that's the report. Deliverable 3 is just your reflective paragraph. Both of those are due on the 9th, and our final, remember, it's on a Tuesday, and it's a little later than what we normally meet. It's on Tuesday, the 15th of December, and it's from 6 to 8. We are trying to get through Chapter 7. Hopefully we will do that by Wednesday. But what we're doing now is we're essentially factoring operators. We're trying to break those up into parts or pieces. And one of those parts is a scaling part. Does this operator scale? Does it expand or contract? And does it rotate? In terms of if it's operating on a vector, what can it do with that vector? It can maybe turn it, rotate it, and it can expand or contract that vector. And we want to now understand how we can factor these matrices, and we're doing it by means of a positive operator and an isometry, where the positive operator is a scaling and the isometry is a rotation. And I want to just recap those definitions before we then start talking about these isometry operators in complex inner product space and in a real inner product space. An isometry in a complex inner product space will have all of its eigenvalues of magnitude 1, or you could sort of think of those on the unit circle. But if you're in a real inner product space, then we could either go exactly in the same direction, we could flip 180 degrees, that's this 1 and minus 1, or we could do this rotation, and that's when we could have a 2 by 2 or a 2 by 2 subblock that doesn't possess real eigenvalues, and those then are associated with a rotation. And that's where this rotation matrix, that's what this cosine sine matrix does, is it rotates objects, and we'll try to maybe explain that or look at that in today's class. So those are relative to isometries. We will then try to motivate polar decomposition. That's what we're calling this factorization of an operator into a scaling piece and a rotation piece. We will try to motivate that by generalizing complex numbers. And complex numbers, you can think of those as being written in rectangular form or in polar form, and in the polar form is more conducive to this angle or rotation and scaling, with the magnitude scaling and the angle rotating. The polar form of complex numbers, and we'll do that by thinking about what we were saying was analogous, or how can we generalize a complex number? Oh, that's a linear map. But then we said, what's the conjugate look like? And we said that was, or what's a complex conjugate of a complex number? What does that correspond to in a map? And that was the adjoint. And so we'll continue with those kinds of generalizations to try to motivate the polar decomposition, which is now going to be presented as the linear map T can be factored into a direction and a scaling, an isometry, and this basically positive square root of T dagger T, where T is the original linear map. That leads us naturally into thinking about what are some ways of measuring this scaling amount, and that's singular values. The singular values of t, they're different from the eigenvalues of t, obviously, since the singular values of t are the eigenvalues of this normal operator square root of t dagger t. Once we have singular values, we can then introduce another decomposition of a matrix, which is singular value decomposition, and that now allows us, now we've made it to the point where we can talk about pseudo-inverses, which was a question in August. I don't know when it was, but now we can talk about a pseudo-inverse using the concepts that we've developed, and one of the fallouts from singular value decomposition is the fact that you can now do a pseudo-inverse with that singular value decomposition, and we'll give some examples of that. Recapping, a positive operator, you can just think of scaling, and it really has two pieces. If you're given a linear operator on a vector space V, if it's positive, then it's self-adjoint, which means that t is equal to t dagger, or the map is equal to its adjoint, and we have this non-negative property on the inner product of TV with V. So if we have a positive operator, then it satisfies these two conditions. That's our positive operator. If we have an isometry, then it essentially does this norm preservation. If we have this linear operator on a vector space V and it's an isometry if the norm of SV is the same as the norm of that original vector V. And that's true for all vectors V in our vector space. So with this linear operator S, we are not changing the size of this vector in any way relative to the norm. We're just changing its direction. Here are some characteristics. I was just going back through the notes, and hopefully you've watched the previous material or the previous lecture, or at least looked at the notes. Here are some facts that you can keep in mind when we talk about isometries. They are norm preserving. By that I mean what's in black, that the norm of SV is equal to V. It's a generalized rotation. If you think in terms of one-dimensional concepts, a rotation is really just what can you do in one dimension. You can go either forward or backward. That's the 1 and minus 1. It's injective, which means that all of these isometries, if it's injective, then what do we know about the null space? It's trivial, isn't it? It's the zero vector, which now means that that map is invertible. It preserves inner products, meaning if we put this S and operate it on U and V and form their inner product of SU and SV, that's equivalent to the inner product of U and V. It also preserves orthonormality, which means if we have a collection of orthonormal vectors E sub j, then the set of vectors E or S E sub 1, S E sub 2, up through S E sub n would also be an orthonormal set. It doesn't change these orthogonality of the original vectors, meaning they continue to be orthogonal to each other, and these isometries are normal, meaning S dagger S is equal to SS dagger, or S and its adjoint commute. These are some facts or properties of isometries. So starting with that, let's now look at what these isometries mean or correspond to relative to a complex inner product space or a real inner product space. Let's start with the complex because that's usually less involved or a little simpler. Let's say that we now have a vector space V that's a complex inner product space. And let's assume that we have this operator S that's a linear operator on that complex inner product space. That operator, that linear operator S, is an isometry if and only if there exists an orthonormal basis of the vector space V, and those vectors, those orthonormal basis vectors of V, are actually eigenvectors of the linear operator S, consisting of eigenvectors of the linear operator S, with all of the eigenvalues of that operator S having absolute value or length 1, with all corresponding eigenvalues, I'm just going to say the magnitude of lambda sub I equal to 1. The last time we actually showed B implies A, meaning if we start with this orthonormal basis of eigenvectors of S with all of those eigenvalues having a magnitude of 1, then that gives us an isometry. Let's now show the other direction on this if and only if, that A implies B. That if we have S as an isometry, that implies that we have a set of eigenvectors that are orthonormal and they have magnitudes of those eigenvalues equal to 1. So let me just try to say what I just said, or let me write what I just said. We showed if the eigenvalues all have a magnitude 1, then this linear operator S is an isometry that was from an earlier example, and now what we want to do is go in the other direction. Which, if we view the first statement as A and the second statement as B, A implies B. Which now says, okay, let's assume A, and A was S is an isometry. If S is an isometry, then we have all of these characteristics, I through VI, 6 characteristics, and the one that we want to use right now is the last one. That if S is an isometry, let's now play on the fact that it's a normal operator. Assuming S is an isometry, then that implies that S is normal. Again, S and its adjoint commute. That's what we mean by normal. Once we have a normal operator, what do we know about the eigenvectors? What's the spectral theorem tell us? If we have a normal operator, then that tells us something about those eigenvectors. They're now, it can be diagonalized, and they're going to mean then that they are orthogonal, and we can normalize them if we're in an inner product space to be normalized so that we can have orthonormal eigenvectors. Thus, the spectral theorem says there is a basis of orthonormal eigenvectors when we have a normal operator. If we have eigenvectors, then we have eigenvalues. Let's just pick one. Therefore, let's just select or let lambda sub j be an eigenvalue associated with this orthonormal eigenvector E sub j. So now we've just matched up the eigenvalues with the appropriate or corresponding eigenvector. What we want to do now is see if we can learn something from the absolute value of lambda sub j. Is it okay if I said that the magnitude of lambda sub j is the same as lambda sub j E sub j? Is that okay? Remember, if we squared that norm, we ended up with just the scaling. This is, remember, E sub j is an orthonormal vector. So if we took the scaling, which is the lambda, and scaled an orthonormal vector, then the norm squared is just the absolute value of that scaling squared. Here we're just looking not at the square, but the unsquared version of that concept. So this is coming to us, or this is allowed, because E sub j is an orthonormal vector. But now that we have lambda sub j E sub j, that's telling us that we're scaling this eigenvector by the eigenvalue, and that's exactly what the operator times that particular eigenvector gives you anyway, meaning this is equal to S E sub j. That's the definite, and we are assuming that E sub j was the eigenvector associated with lambda sub j. But what did we assume in the A direction, or what was the A statement? We're assuming that S is an isometry. So now we have this norm preservation property. SV's norm is equal to the norm of V. This is now equal to the norm of E sub j. That's the definition of an isometry. And what do we know about the norm of an orthonormal vector? Since it's been normalized, we normalized it to have a norm of 1, and this is true for all j, and now we can go to the far left, that's equal to the far right, and now we've just shown that the magnitude of all of these eigenvalues for this operator that's an isometry has a magnitude of 1. So that's for a complex inner product space, that an isometry, a linear operator is an isometry if and only if it has an orthonormal basis of eigenvectors and each of the eigenvalues have magnitude of 1. So that means that if these eigenvalues are, if you're thinking about those as scaling, they're not scaling at all, are they? They have a magnitude of 1. Let's see what happens when we change our vector space to be a real inner product space. Now we have another theorem for that. That's theorem 38. And that says for a vector space V, which is a real inner product space, and S again is a linear operator on that real inner product space. That operator S is an isometry. Again, this is an if and only if clause. If and only if there exists an orthonormal basis of V in which this linear operator S is not quite diagonal. It can be block diagonal, meaning we don't have necessarily 1-by-1 blocks on the diagonal. They could be some 2-by-2 blocks. This linear operator is block diagonal with blocks of 1, -1, or a 2-by-2 block with the 1, 1 being the cosine of theta, the 1, 2 being minus sine theta, and cosine theta in the bottom row, where theta now is this angle between 0 and pi. Actually, it's just a little bit to the right of 0. If it was 0, then we would have a 1-by-1 block. So that's an open interval on the 0. This is now what happens. We don't have this nice diagonal property of the eigenvalues. We could have 2-by-2 subblocks that don't have real eigenvalues when we're talking real inner product spaces. And then those blocks are basically a rotation. We aren't going to prove that result, but we will try to interpret it. Or talk a little bit about the structure that's now imposing. To try to get a little bit of understanding from that. If we have a 1-by-1 block or 1-by-1 blocks in this real inner product space, that now gives us, and now I'm going to sort of be lazy and say eigenvector / value. So that's eigenvector / eigenvalue. And the magnitude of those eigenvalues for an isometry, if it's a 1-by-1 block, that's just 1. Which really means when we're dealing with the real inner product space, our only option for these 1-by-1 block eigenvalues are for those eigenvalues to be either +1 or -1. If we can't find an eigenvalue for these 2 by 2, these rotation pieces, then what happens? For the 2 by 2 blocks, they actually correspond to two-dimensional or 2D invariant subspaces. That's always a possibility when we're dealing with real inner product spaces. And that block now has the form of a rotation matrix, which really says that then this isometry is still in play. It's still a generalized rotation. And in that theorem, we showed the form to actually be of the structure A minus B, B, A. When we have a normal operator. So now what we want to show is for that 2 by 2 case, can we actually demonstrate that the norm of this isometry in a real inner product space with E1 is equal to 1, where E1 is now a vector associated with this 2 by 2 rotation. Here's our verification. So we know that if we had this isometry S and we had two vectors that are orthonormal, that's what we're saying here. We have an orthonormal basis. E1 and E2 are the pair that we're interested in. And those then tell us that if we use E1 and E2, that will allow us to re-represent this isometry as this 2 by 2 block, in the first row A minus B, and in the second row BA. Now if we applied that 2 by 2 submatrix to E1 and E2, what does that do to the first column? Or what's the first column of that product on the right? If we think of how that matrix weights the columns, then we're weighting E1 by A, and we're weighting E2 by B, meaning we now have A E1 plus B E sub 2. That's the first column, and the second column is minus B E1 plus A E sub 2. And I hope it's clear that this piece is really just SE1, and this piece is SE2. If we just look at what happens on the left, that's equal to what's on the right. Now, what happens when we look at the norm squared of SE1? We said SE1 has to be AE1 plus BE2, and so let's just look at its norm. squared. But what do we know about E1 and E2? Those were orthonormal, which now says if we have this linear combination of orthonormal vectors, what's the norm squared going to be? It takes the weighting on those orthonormal vectors, and what does it do to each of those weights? Takes their, if this was complex, it's actually real, but in the complex case, it says take the magnitude of one of those scalings and square it, plus the magnitude of the other scaling and square it, and just keep going. Here we only have two orthonormal vectors, so this should be equal to the absolute value of A squared plus the absolute value of B squared. But A and B are actually real in this complex, or in this real inner product space. So that means that this is really just A squared plus B squared. And what do we want that to equal? We needed that to equal 1. We needed the norm of SE1 to be 1, so the square of that is also equal to 1. And when is A squared, or what's one way of finding an A and a B where A squared and B squared equal 1? So they could be on this unit circle, couldn't they? Or you could say that now, relative to A, we could figure that as cosine of theta, and B is sine of theta work, and that now if you plug those in to the appropriate locations for A and B, we have cosine theta minus sine theta, cosine theta. So we've sort of shown where this 2x2 block structure arises, or how it can be put into play. These isometries then allow us to think about rotating vectors and not changing any of the scaling. We've talked about positive operators. Yes? So now, can you have an isometry for a 3x3 matrix? Yes, you can. It's just now, what do you know? Now you know one of those, with a 3x3, you could have it purely diagonal. If it is, then the norm of those eigenvalues are 1 or minus 1. Or you could have one being a 1x1 block and another one being a 2x2 block. Then the 1 block would be either 1 or minus 1, and the 2x2 block of that odd isometry, that third order isometry, is now having this structure. So you can have isometries that are any size, but now you know they have to be square. These are operators. But they could be any integer size. Does that answer your question? So the question was, can we have a third order isometry? And we can. It's just now, if you have odd, it's possible that you could have 2x2s in making up that odd number. So if it was 5, you could have 2 2x2s and 1 1. You could have 5 1 1s. You could have 3 1 1s and 1 2x2. So it's all these different combinations that you might have, but they all are made up of these really 3 pieces. So now the rotation matrix, yes, the rotation matrix will be always this simple. So the rotation, the 2x2 rotation always has this structure. It's always going to be cosine theta minus sine theta.
If we consider 3-dimensional, then the rotation matrix will be like about some particular axis.
So now, well, it's going to be, now, so don't overthink this. I think it's maybe what you're trying to do, and I'm trying to now say, you have now identified 2 orthonormal vectors, and now you're in a 2-dimensional space. So now in that particular, those two directions, they just map out a plane, and now you're rotating in that plane. In the other orthonormal directions, you're either staying in that direction or just reversing. So you always have just a 2D, two-dimensional rotation in these real inner product spaces. Is that helping? So don't make it seem more complicated. If it's fifth order, now really as complicated as it gets is you might have two planes that have rotations on them, but those two planes are orthogonal to each other, and now you have another one that's just going in the same direction or it's reversing 180 degrees. But you always have these rotations in a two-dimensional plane that's defined by these orthonormal vectors. Okay, so now we have isometries, which are rotations, and we have positive operators, which allow us to scale. What we want to do is piece those together to essentially factor any linear operator. What I'm trying to do now is motivate. So let's say that this little piece is motivating what we will eventually call polar decomposition of a linear operator T on a vector space V. This has nothing to do with the fact that it is getting close to the end of the year and maybe it's colder. Doesn't have anything to do with the poles, but it has something to do with polar representation of complex numbers. So you could think in terms of polar coordinates, but now we're really only talking about magnitudes or scaling and angles for our complex numbers. Here, what I want to maybe say is this polar decomposition, we are combining positive operators and isometries as factors of this linear operator T. That's the underline, that's the polar decomposition. You can think of it in that way. And what I want you to also keep track of is recall all of these analogies that we've been trying to introduce along the way between numbers, complex and real, and what those might look like in terms of operators. For example, suppose that we had just a complex number. So Z is a complex number. What did we say was analogous to that in terms of an operator? So now in terms of just a complex number Z, now that's this 1 by 1, but what was if we simplified it so much that we had a one-dimensional operator, I just gave it away maybe, we're trying to think of this as just being a generic operator, wasn't it? T, it's a linear operator T. So this was analogous to T being a linear operator on a vector space, V. Maybe I made my analogous arrow a little too big. I may squish it down in the next few rows so that I can have more room to write. But I have an infinitely wide paper, but you don't, right? I can keep going into the right direction. What if we now said, what if we look at the complex conjugate? if we've now established this analogy for A, that a complex number is analogous to just a generic linear operator on a vector space, if we now looked at the complex conjugate, Z star, what did we say that was analogous to? If Z is T, what was the complex conjugate in terms of operators? That was the adjoint, wasn't it? So that's T dagger. So now when we start playing with all of this, when you see Z, we think T. When you see Z star, you think T dagger. What's another one? What if we had a real number? Then we're saying that Z is R. How are Z and Z star related? They're the equal, aren't they? If it's real. And what did that correspond to in our operator? Then it was self-adjoint, wasn't it? We had T is equal to T dagger. So if we had a complex number and it was equal to its complex conjugate, then that in operator think, that says that we have a self-adjoint operator. What if we had a non-negative real? Which we represented as Z greater than or equal to 0. What kind of an operator then did we have? Now think of that inner product of TV with V. We needed that to be non-negative, and it was real. So that now that means that T was what? Positive, wasn't it? So now we have this positive operator, which is maybe, the book says, is maybe a little bit misleading. It's really a non-negative operator. But the convention is to just call it a positive operator, so we're just living with the convention. And we just recently maybe, well, talked about, we didn't introduce it so much with respect to the analogy, but now we can. What if we said that the absolute value of that complex number is 1? What kind of an operator now do we have? Pardon? We had an isometry, which is a normal, right? So this one was the isometry. We had all the in a complex inner product space, all the eigenvalues were equal to 1. We could have complex eigenvalues. Their absolute value is 1. That's an isometry. So now a normal operator, what's a normal operator? What did we say? So if we have an isometry, then we know it's normal. We could have a normal operator that's not an isometry. But if it's an isometry, it is normal. So now, what are we wanting to do? Now we want to use these analogies to try to infer some relationship on operators that we already understand with complex numbers. Can I use any more motivating words. Now we're going to be inspired by this analogy. Or take note or remember that any complex number as I've mentioned already in today's lecture, can be expressed in polar form. Meaning, if I start with a complex number, now I'm going to just play some tricks with algebra. Meaning, the complex number is equal to z, but I can always multiply a number by 1 and not change it. And the 1 that I'm going to use is the length of that complex number, or its modulus, divided by its modulus. So I'm just multiplying z by 1. But now I can, since that's equal, I can move those pieces around. Now I have a jigsaw puzzle, and I can just kind of shuffle those pieces on the right-hand side, and I can say, well, that's the same as that. It's just now I'm sort of regrouping so that the first grouping is really I'm just normalizing the complex number, z divided by its modulus, or z divided by its amplitude, and I can write the absolute value of z as z squared, or z conjugate times z square rooted. Because what's z conjugate z? That's like a squared plus b squared. And if I take the square root of that, I'm going to get the length of that original complex number, a plus jb. Meaning, I'm going to rewrite the absolute value of z, or the modulus of z, as the positive square root of z star z. Meaning I started with just any old complex number z, and I ended up writing it as a product of two pieces. And this first parenthetical piece is how big is it? Or where is it? If you plotted that point on the complex plane, where would that live? Z divided by its modulus. It's on the unit circle. So this one is on the unit circle, or that's like a direction. It doesn't have to be in the x direction or the y direction. It can be anywhere. And this second piece is really just giving us the length of that original complex number z. That's the square root of a squared plus b squared. Now that left-hand side complex number equaling the right-hand side is trying to inspire us. It's trying to inspire us through all of these analogies. Meaning, if I now replace z on the left with an operator t, that's the analogy. Then I'm going to start replacing some of these other pieces. I know what the complex conjugate of z is analogous to. That's analogous to the adjoint of t. I also know what's analogous to a complex number that's on the unit circle. What kind of an operator is that? That's a direction. And that's what we said an isometry does. So, what I'm trying to get at is this expression would suggest that any complex number, or that any operator, on some vector space V can be written as Z is just T, that's the left-hand side, and now the right-hand side, I need that to be a direction, which is an isometry S, and now I can talk about the positive square root of complex conjugate of a complex number, and that's the adjoint of T, and the number itself was T. With S being an isometry. This is now a direction, and this piece is a length. So now we've been inspired by just the polar form of a complex number, and now we've been able to factor a generic linear operator into a direction and a length. And we know how to, or we will learn how to produce this direction, this isometry, and this length. We already know how to find, starting with an operator, we know how to find its adjoint. We've talked about finding the unique square root of a T dagger T expression, or a positive linear operator. Now we'll learn how to find this direction S. And yes?
Assuming that T is positive?
So now, is this assuming that T is positive? Did I say anything about the complex number Z that I pulled out of a hat? No. So I'm not assuming, I'm just assuming that T is a linear operator on a vector space V. That's all that's the assumption that I'm making, that it's an operator. So now we're dealing with a square. If we were looking at its matrix representation, a square matrix, but that's all that I'm talking about. So we're not restricting this linear operator to be any particular flavor. It can be anything as long as it's an operator, which means that it maps from the vector space back into the vector space. What we have to do, so we could find its length, and then if it was negative, we're just going to go 180 degrees in that direction. And that's what we're going to show. So this inspired factorization of a linear operator into a direction and a length can happen. I wouldn't have spent this much time talking about it if it wasn't. So indeed, this factorization works. And that is expressed in terms of Theorem 41. And that's the polar decomposition. Which says if T is a linear operator, and that's all we're restricting it to being, is a linear operator, then there exists an isometry S, which is a linear operator on that same vector space, such that this original operator T is equal to this isometry S together with the positive square root of T dagger T. So let's sort of break this theorem down into some of its pieces. And if you put all of these pieces together, it sort of forms a proof. First, let's start with T being a linear operator on V. If we pick any vector, little v in capital V, then if we looked at the norm squared of TV, how have we learned to write that or express that in terms of an inner product? How would we write that? That's the inner product. We're assuming we're on an inner product space. So now we have TV inner product with TV. But we can also write T as T dagger dagger. So let's do that with the T in the second slot. So this is now TV inner product with T dagger dagger V. Now, if we use the adjoint definition of, well, just the adjoint definition, we can now slide that operator in the second slot into the first slot. And what's it going to look like if we do that? How can I rewrite that most recent inner product? If I now want to move that T dagger dagger operator into the first slot, it's now coming in daggered, isn't it? Or losing the dagger, one of the daggers, so that now I have T dagger T V inner product with V. That's just the adjoint definition. But now I know that T dagger dagger is nice. T dagger T, what did I say? I wanted to say T dagger T. So T dagger T is normal, and from these previous theorems that we talked about, Theorem 27 and Proposition 28, we can split that T dagger T into a product of square roots. So that now let's rewrite T dagger T as the square root of T dagger T times the square root of T dagger T. And that's coming to us from these theorems and proposition and the fact that T dagger T is normal. Now we can slide one of those operators into the second slot, and we know that the square root of T dagger T is self-adjoint, so that it's equal to itself, which means when we slide it into the second slot, we end up with something like that. Again, we're applying the adjoint definition and the fact that that positive square root of T dagger T is self-adjoint. But what is that now? That's the definition of our norm squared, isn't it? Of square root of T dagger D operating on V squared. And if we compare the first expression, which was the norm squared of TV, with the last expression, the norm squared of square root of T dagger TV, what's that telling us about sort of this? Well, let me just say, therefore, we have the TV squared is equal to the square root of t dagger t v squared. What does that tell us about how TV scales relative to the square root of t dagger t squared scales? If we operate on any vector v, which we said just pick any vector v, and we operate on it with t, how is that operation going to scale relative to the square root of t dagger t operating on that same vector based on this result? It's not going to do anything different with the scaling, is it? So if it expands it by a factor of pi cubed, then the square root of t dagger t is going to expand it by the same factor. We're not saying that it's not expanding or contracting, but if it does, it's doing it by the same amount. That's what that's telling us. So, the square root of t dagger t, which is the positive square root of t dagger t, has the same effect on the norms of t. And that's good because our factorization had an isometry times the square root of t dagger t, and that isometry we know doesn't do anything to the norm, does it? So if t is now split into two pieces, with one being an isometry and one being the square root of t dagger t, the isometry is not going to change the norm. So the square root of t dagger t luckily keeps preserving the scaling behavior of t. Meaning, therefore, the positive square root of t dagger t in the factorization is going to work the way it is supposed to work. But is there such an S? Is there an isometry that allows us to conclude that we can factor this linear operator t into this isometry and square root of t dagger t? The idea that we're looking at then is actually sort of in two pieces. We didn't say anything about t, did we? T is generic. T could be, it could have a null space, a non-trivial null space. We didn't say that it had an inverse, did we? Or that it was injective or surjective. We didn't say anything about T. So we maybe have to think about what's happening, or the range space of T may not fill the entire vector space V. It may not be surjective, which means that this isometry that we are going to build is actually going to be built up in two pieces. One piece that's only working on the range of T, and the other isometry piece that's working on the orthogonal complement of that, and then we'll just put those two pieces together because they're on working in orthogonal or in this sort of direct sum decomposition. So here's the idea. One, we want to create one isometry, S1, such that the range of T dagger T maps onto the range of T, and then we want to extend that in the orthogonal complement to the range of T with another isometry. We want to extend S1 to the actual isometry that we need, S. First, then, let's work on S1. That's the biggest piece of this. So let's now define a map, an isometry S1 that takes the range of the square root of T dagger T to the range of T. And again, just sort of think about rotations. We're now going to be finding this square root of T dagger T as an operator, and that may actually sort of bend or move things around, and we want to sort of correct those or push them back into the range of T. Meaning, what we're doing now is we're creating this map S1 that takes as an input a vector that is formed from the square root of T dagger T operating on V. This is now the input to this map S sub 1. And we're using this relationship to define S1, where that needs to equal T with V. We need these to be the same. And this is the output of S1. And again, think of S1 as just a rotation. So maybe the input to S1 starts on the x-axis and the output maybe ends up on the y-axis. So we're just doing a rotation. That's S1. The hope is that we can extend S1 to an isometry meeting our needs for S. So here's sort of another way of thinking of that. We want S, or the fact that we're saying S square root of T dagger T equaling T, what that really means is that S square root of T dagger TV is equal to TV for all vectors in our vector space V. So when we say that we're factoring t into an isometry S, square root of t dagger t, that's really meaning that we have this relationship. But we defined S1, that's how we defined S1, is to produce this. We want S1 operating on this vector to be TV. And that vector that it's operating on is just the left-hand side of this. So we have actually created or defined S1 to satisfy this condition. S1 has been defined to make this true. What we want to do now is see if S1 sort of is nice. Is it behaving the way we want it to behave? But does this make S1 a well-defined linear map? So we want it to be a linear map and we want it to be unique. If that's the case, let's check some of these pieces. Let's check uniqueness of this map. Check uniqueness of this map S sub 1. Statement: if the square root of t dagger t v1 equals square root of t dagger t v2, then we better end up with tv must equal what? Or tv1 must equal tv2. So we want to make sure that that statement is true. And the assumption is that the square root of t dagger tv1 is equal to the square root of t dagger tv2. So now let's look at the norm of tv1 minus tv2. But t we assumed was a linear operator. Meaning we can now combine v1 and v2 algebraically before we operate on those with t. And what do we know about t operating on a vector relative to its norm? And the norm of the square root of t dagger t. It's preserving the norm, so now we have this is v1 minus v2 norm. But the positive square root of t dagger t is a linear operator, and so we can distribute it or break apart the v1 minus v2. But that's exactly, or we said that square root of t dagger tv1 was equal to the square root of t dagger tv2. So this norm better be 0, which now allows us to say that the norm of the first expression is 0, which now says that tv1 is equal to tv2. So that proves our uniqueness. Now what we want to do is say something about the linearity of that, and then we will start to clean up or extend S1 to this isometry S by creating another S sub 2 isometry. And I'll pick up with that on my own, but you'll get to watch or listen to that. We won't meet on Wednesday.